Okay, let us talk about series. 11.2. Series are everywhere. The solutions for ordinary and partial differential equations, time series in computer science and data analysis, in engineering, they are everywhere. So it's very important for us to learn the definition of series and learn the techniques to analyze those series. But they are kind from sequences. There is a connection between series and sequences. Let's start defining a series. Let AN be a sequence. So we start by taking the terms of a sequence. A sub 1, A sub 2, A sub 3, and so on. These are the terms of our sequence. A series is constructed by adding the terms of sequence A sub n. So you have a sequence, you're taking those elements, those terms, add them together and define something new, and we call it a series. So A sub 1 plus A sub 2 plus A sub 3 plus dot, dot, dot. This is denoted by sigma A sub n, n starts from 1, goes to infinity. This is summation notation, we call it sigma. N is equal to 1, A1. Summation means plus. A, next A is equal to 2, we get A2. Summation plus. Next N is 3, A sub 3, then summation plus, and so on. So this series takes all the terms of a sequence, add them together. Okay. Well, to define something new, we're interested in knowing when this series is convergent, when it is divergent. Well, we say that series AN, n starts from 1 to infinity, is convergent if the limit of its partial sum exists. What is a partial sum? Before the partial sum this way, we take just partial sum of this series, of this sum, just a partial sum, some part of it. This partial sum is defined as S of n, which is equal to the sum of A sub I starts from 1 to n. We take the limit of S of n. If the limit exists, we say that this big series is a convergent series. S sub n is equal to the sum of A sub i's. I starts from 1 to n. So guys, again, being convergent and divergent for a series is different from being convergent and divergent of a sequence. Do not confuse them. It's very important. It's usually a challenge for students to distinguish between a sequence and a series, being convergent, being divergent. So give us an example so we can distinguish between a sequence and a series. Very well. This is a famous example that you can always use when you're analyzing a sequence and a series, then you get confused. So example. Remember that I defined this sequence as an to be 1 over n. Remember that this sequence is a convergent sequence since the limit of 1 over n as n approaches infinity is 0. It means that this sequence is a convergent sequence. This sequence is convergent. We just learned the definition of a series. If I take the terms of this sequence, add them together, I can define a series, a new mathematical object. So the terms of this sequence, A1 is 1, A2 is a half, A3 is a third, A4 is a fourth, A5 is 1 over 5, and so on. As a series, we are adding the terms of a sequence. What sequence? Let me take this sequence. Okay, why not? A1 plus A2 plus A3 plus dot, 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 or the summation of an and starts from 1 to infinity. So it is 1 plus a half plus a third plus a fourth plus the rest of the terms, which is the summation of 1 over n and starts from 1 to infinity. By the way, the name of this series is harmonic series. This is a very famous series, harmonic series. Okay, what is the partial sum for this series? To check if this series convergent or divergent, we need to check the partial sum. Partial sum is S sub n, which is the sum 1 over I starts from 1 and stops at n. Okay, just take the first n terms, add them together. 1 plus a half, this is 3 halves. 1 plus a half plus a third is 3 halves plus a third, which is equal to 11 over 3. Okay, 3 halves is less than 11 over 3. You can continue this process. By adding the partial sums, you see these numbers are getting larger and larger. 1 plus a half plus a third plus a fourth. This is 11 over 3 plus 1/4. 44 plus 3, 47 divided by 4. As you can see, these numbers are getting larger and larger. So the partial sum shows a divergence behavior. since S of n is not convergent, the series is not convergent. You can continue this process. You can add the rest of the terms, the rest of the partial sums, and check the relation between them. These numbers are getting, these sums, these partial sums are getting larger and larger. So it means that this guy is a divergent series. The sequence is convergent, but the series coming from that sequence is divergent. Guys, we fixed the fractions. I made mistakes when I took the common denominator in the first one. So please fix that. These are the partial sums. Okay, two important series and their sums. So the very first one we talked about is harmonic series. You can always use harmonic series as a divergent series. And please make sure to correct these sums. Important series. The very first one is geometric series. Well, geometric series says if you have A plus A times R plus A times R squared plus dot, 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 and it's equal to sum A R to power n minus 1 and starts from 1, goes to infinity. This sum is equal to A over 1 minus R with the condition that R is less than 1. Geometric series. For example, suppose the question says, check to see if the following series is convergent, divergent. We have 5 minus 10 over 3 plus 20 over 9 minus 40 over 27. What's the rest of the terms? Okay. Well, let us try to analyze this series, see if we can see any similarities between this series and a geometric series. This is 5 minus 5 times 2/3 plus 5 times 4 over 9 minus 5 times 8 over 27 plus the rest of the terms. So as you can see, your A is 5. What about R? Okay, R, if we just move this negative sign next to 2/3, it is negative 2/3. Negative 2/3 squared, negative 2/3 to the power 3, and so on. So this guy can be written as 5 plus 5 times negative 2/3 plus 5 times negative 2/3 squared plus 5 times negative 2/3 to the power 3 plus the rest of the terms. So I have my A as 5 and my R is negative 2/3. And as you can see, the absolute value of R is less than 1. Absolute value of negative 2/3 is 2/3. which is less than 1. So based on the definition of geometric series, the sum is A divided by 1 minus R. This is equal to A, which is 5, divided by 1 minus negative 2/3. So I get 15 divided by 5, or just 3. The sum of this series is equal to 3, because it is nothing but a geometric series. Other than geometric series, we have a series that we call telescopic series. I'm going to give you one example to see the behavior of a telescopic series. Example. Suppose you have a question about these types of series. The series 1 divided by n times n plus 1, and starts from 1 and goes to infinity. You have a series, and the question is this series convergent, divergent? If it's a convergent series, what is the sum? Very well. From elementary calculus, you learn that you can use partial fractions to split this guy. Recall 1 over n times n plus 1 using partial fractions. Guys, partial fractions are going to appear in differential equations as well. So if you need to review those materials, please review them. It's a divided by n plus b divided by n plus 1. So it means that a times n plus 1 plus b times n is equal to 1, or an plus a plus bn is equal to 1. So if you factor out n, a plus b plus a is equal to 1. It doesn't have variable n on the other side. It means that the coefficient for n was 0. So 0n plus 1 is n times a plus b plus a. So it means that a plus b is just 0, and a must be equal to 1. So a is 1, a plus b is 0. By substitution, b is negative 1. So this series, if we form the partial sum, it's going to be the sum. I starts from 1 to n, 1 divided by I times I plus 1. This guy can be written as the sum 1 over I minus 1 over I plus 1. This is your partial sum. And I starts from 1 and stops at n. Let us start plugging in values for I to see the behavior of the partial sum. I is equal to 1, so you get 1 over 1 minus 1 over 2. So I is equal to 1. I is equal to 2, you get the second addend, which is a half minus a third. If I is equal to 3, you get a third minus a fourth, plus the rest of the terms. So this is I equals to 3 plus the rest of the terms plus, and if I plug in n, I get 1 over n minus 1 over n plus 1. So before this addend, if we plug in n minus 1, we have 1 over n minus 1 minus 1 over n plus 1 over n minus 1 over n plus 1. So this is when I is n minus 1, and this is when I is equal to n. So let's take a look at this sum together. 1 minus a half plus a half. These two are opposite of each other. Cancel out. Negative a third, positive a third. Cancel out these two terms. Negative a fourth, the next term has positive a fourth. We already know that. And we can continue this process. We can cancel out all of these terms. This term is going to be canceled out with the previous term, and negative 1 over n and 1 over n. So what's left in this partial sum? In this partial sum, what's left is the very first term, which is 1 over 1 or 1, and the very last term, which is negative 1 over n plus 1. Well, if you take the limit of the partial sum while n approaches infinity, this is going to be 1 minus 0, which is 1. This is the sum of our series.